Okay, we're going to start on a new topic now called acid-base chemistry. And the reason why we study this is because there's a large number of chemicals that we interact with, whether it's in our bodies or at home, where we have acids and bases playing important roles. So a lot of the genetic material, for example, DNA, RNA, those are all ribonucleic acid. And so there's certain type of chemistry they do that we can understand by understanding the chemistry of acid. In addition, we also have foods that we eat, the different types of solutions that we use at home, like for cleaning and for other purposes. They are all examples of acids and bases, and that's why understanding acid-base chemistry is going to have important applications in any type of chemistry you go into. So the first thing we want to talk about is just the definition of acids and bases. And it turns out there's three different definitions, and this went in chronological order. So we're going to start with the Arrhenius definition, a name that hopefully sounds familiar to many of you because we have first discussed him in Chem 11 when we talk about those electrolytes, non-electrolyte type solution. And in fact, that was the study of acids and bases was one of the reasons why that definition came about, the electrolytes, non-electrolytes. But also when we talk about rate, there's the Arrhenius equation. Now we're talking about acids and bases, and we have Arrhenius again. Arrhenius defined acid as a compound that will dissociate in water to produce H+. Now we know that these are all covalent compounds. They're covalent bonds that are formed between the proton and the rest of the molecule, and then when you put water in there, it will dissociate to produce H+. That's a unique property. Typically, we don't expect covalent compounds to produce ions, but acids do. So examples of acids are, you might have remembered this from studying nomenclature, anything really that contains H and has aqueous solution as the phase here because it has to be mixed with water in order for it to produce the H+. Now, the H+ ion itself is the smallest atom in the entire periodic table. Now it has a full charge on it, so it's a supercharged small particle. As a result, it's not going to be stable on its own. It's going to want to immediately quench that charge. That's just the way the universe works. Everything wants to be neutral charge. And so it's going to look around for something that has a negative charge around it, and water is floating around. And water, of course, is oxygen, which has a couple of lone pair electrons around the oxygen. So that lone pair electrons can then bind and neutralize the charge on the proton, forming this new species that we call the hydronium ion. And that's the species that we actually see. We usually just write it as HCO+. However, you will see in a lot of reactions that I'll be writing later on, as well as in many textbooks, that the H+ symbol is still used to represent the H3O+. So another way to say this is H+ and H3O+ are representing the same species, which in this case is the hydronium ion. Now, a base, by the Arrhenius definition, is just ionic compounds, in this case, that produce hydroxide ion when dissolved in water. So the standard bases that you know of are the sodium hydroxides, the barium hydroxides. Any soluble hydroxide salts is really a base based on the Arrhenius definition. A neutralization reaction is a reaction where you have a base and an acid reacting together, and the hydroxide and the proton neutralize each other to form water and salt. And so this hopefully is something that's familiar to everybody. HCl plus NaOH, which could be written as the separated ion forming the NaCl and H2O. The net ionic equation itself is just H plus OH minus goes to water. There is a major problem with the Arrhenius model, and which is that it can't really deal with the presence of weak bases where there is no hydroxide present. An example would be ammonia, NH3. In the Arrhenius theory, all bases have to contain hydroxide, but ammonia doesn't. So how do we explain that ammonia acts like a base, neutralizes acids and so on? The chemists at the time had thought that perhaps it's not ammonia that exists in water, but ammonium hydroxide, which has the formula NH4OH. And so that would explain why it's a base, because NH4OH can break apart into NH4 and OH minus, and OH minus, of course, is the Arrhenius characteristic of a base. It turns out that when they tested for the presence of NH4OH, there's very, very little of it. So in other words, when you have a solution containing ammonia in it, what we find is there's only ammonia. The actual NH4OH is there, but very, very little. The majority species there is ammonia. So in other words, that whole theory of that it's actually NH4OH that exists in water and thereby producing the hydroxide doesn't really work to explain why ammonia is basic. And so that's the major issue with the Arrhenius theory, and that's the reason why we need to come up with a new definition for acid and base. And the error there has to do with the fact that it's not really thinking of water as an important component in the entire process of acid-base chemistry. So now we have a second definition that does take into account water as an important component, and that's called the Bronsted-Lowry definition. And in this case, we're thinking about acid as a proton donor and base as a proton acceptor. So it's a much more general definition. It centers on this idea of a proton transfer reaction where an acid will give away proton and a base will accept that proton. Another way to think about this is that an acid will never exist unless a base is also there, because nobody will accept that proton from the acid unless a base is there. This change in definition is what highlights the importance of water. Because if you think about that solution of ammonia on its own, it's not going to do anything. But then if you have water present, now you can have a reaction. And so one of the products is going to be NH4 plus, and then the other product is going to be OH minus. So in fact, there is OH minus that's present there, but it's just not in the way that Arrhenius thought about, which is that NH4OH breaks apart into NH4 plus and OH minus, but it's NH3 reacting with water to produce NH4 plus and OH minus. Okay, so again, an acid is a proton donor and a base is a proton acceptor. So going to the reaction here at the example, we have ammonia reacting with HF. Now we know that HF is an acid and ammonia is a base. Now how do we know that? Well, we look at the product side of the equation. So if you look at the product side, you see that the ammonia has now become ammonium. So that means ammonia has gained a proton. The HF, on the other hand, has become F minus, so it has lost a proton. Okay, and then based on the definition of Bronsted-Lowry, if you have gained a proton or you have accepted a proton, that means you're a base. So therefore, ammonia is a base. And then if you've lost a proton or you give away a proton or you donate a proton, you're an acid. So therefore, the HF is an acid. In the Arrhenius definition, HF is an acid, but it's still an acid in the Bronsted definition. So this is just a better definition that captured not only the acid component of it, but also some of these bases that don't contain hydroxide. So going back to that reaction that I just showed you with the ammonia and the water, you can see in this case that the ammonia becomes ammonium, so same thing, so has gained a proton. And then the water, in this case, interestingly, has lost a proton. So here where you can see that the ammonia, it's a Bronsted-Lowry base, and then the water, it's a Bronsted-Lowry acid. With this reaction, the role of water as an acid is critical. If the water is not present, if I just have ammonia floating around on its own, nothing's going to happen. But once you have the ammonia with water, then you're going to have that reaction happen, which means now the ammonia is a base. Okay, so it's really important that you understand that water is a key player in the acid-base reaction. Without water, the acid-base reaction doesn't really happen. Similarly, if you have something like HF, so HF plus water, then becoming F minus and H3O plus. That would be in the Bronsted-Lowry reaction. So again, you would think about the fact that HF has become F minus, and then water has become H3O plus. Well, the HF has lost a proton, and then the H2O has gained a proton. So of course, we call things that lost proton or gives away proton as acid. That's the proton donor. And then the things that gain proton or accept proton, we call a base. So here my water is a Bronsted-Lowry base. My HF is Bronsted-Lowry acid. So you can see that water is critical because without water, the HF on its own will not be an acid. In the Arrhenius definition, we would write just HF as H plus plus F minus. So in the Arrhenius definition, it just seems like the proton will dissociate from the HF and therefore acts as an acid. But now we know better in the Bronsted-Lowry definition that it's the water that's helping to pull that proton off from the HF.